at kinetics, which relates to various interesting terminologies that we explored. First of all, the first video we looked at the aspect of reaction coordinates and how this reaction coordinate explores more about the interaction between reactant and creation of a transition state that arrives at particular product. Now this diagram is quite fascinating because this actually exposes two important terminologies in here. Firstly, we looked at the activation energy, which is the energy difference between the transition state and that of the reactant, and on the other side we looked at the temperature, which is more of the kinetic energy, where we explored more on the collision, the right orientation, and the right bond dissolution, and also creation in the transition state that arrives at the specific product. These two terminologies were really crucial in understanding more on the Arrhenius equation, and this Arrhenius equation was crucial as well because we were able to see the reveal of entropy, which is the pre-exponential factor in this particular equation represented as A multiplied by the exponent, where we actually used the activation energy represented as EA divided by RT, where R is the gas constant and temperature included here. We'll be able to discover more about the rate of a reaction, where to actually solve for that we actually use the ln of the K2 K1 in here equals to EA over R, which is the slope of the line, and this is multiplied by the change in the temperature, which is the inverse of temperature on the x-axis. Now moving into this particular video, we're going to focus now on the rate expression, and the rate expression is actually important in a way because by that way we can actually solve for K later down the line, where K is a rate constant, and this rate constant is actually important in various chemical reactions at specific temperatures. So for a specific temperature we have a unique rate constant of a reaction. Now looking at the first video where we looked at the reaction of triangle with that of circle creating a cone, well, with the help of an enzyme here as a catalyst, but anyways, I don't know why I'm putting catalyst for now, but we'll talk more about catalyst down the line. We actually discovered in here from the rate of chemical reaction that the change in the concentration of triangle and that of the change in the concentration of our circle results in the formation of our cone. So in this case, why am I using negative? Because this is a decay function in here, so as these particular reactants are being consumed, the product is being formed here, and this all is dependent on the change in time for each of them right here. So I'm just using partial derivatives in here, but you can also use triangle as well, but because there is triangle in here, there's kind of discrepancy in terms or consistency in this video here. So now let's look at a specific example, or I will just say a general example. So where we have a capital letter A plus small letter b, capital letter B is going into small c, capital letter C. The small a, B and C's, they are all the number of moles in here, or number of molecules that are involved in this proportioned reaction that leads to the product in here. So what we've figured out that in these three cases here, which is case A, case B, which are all reactants reacting to form one product, which is C, this rate of reaction for the three of these species can be written as the rate is equal to the decrease in the number of moles, which is the inverse of the number of moles of the change in the concentration of A divided by time change is equal to the decrease in the inverse in the moles of B multiplied by the change in concentration of B divided by the time, which are unique in this particular case. And in this other part, since it is the product that is being formed, then there is a change in the inverse in the number of mole multiplied by the change in the concentration of C divided by that same time, or the time interval in there. So that is the general formula for this particular case here, looking at this particular reaction. Now let's look at the first case scenario. The first case scenario in here is going to be looking at hydrogen peroxide forming two products, which are hydrogen water and half a mole of oxygen, or you can do it the other way by just multiplying both sides by 2 in order for we to eliminate the fraction on the oxygen side. So what we see from our experiment in here is that this being the concentration, or which is the molarity axis, and in here which is the y-axis representing the time it takes for a specific reaction to occur, what we notice is that first, as hydrogen peroxide is actually decreasing in concentration, getting to 0 at a particular point, we have the formation of our product in here starting from 0 and approaching first for oxygen 0.5, and then on the other side we have water actually approaching 1 mole per liter in that particular case over there. So focusing on this particular time here, which is just 10 minutes later, where everything kind of stabilizes at this particular region, what we recognize is that to get it constant at T, which is 10 minutes, what we discover is that the rate of each of these reagents first looks at, oh, we have a decay or decrease in the concentration of hydrogen peroxide at a specific time is also equal to the production of water at that same time interval, and also the production of oxygen at that same time interval, where the time interval we'll be looking at is 10 minutes. Then our rate, when plugging in our numbers in here, reveal that first we have our reactant, which is hydrogen peroxide, going from the finish minus the starting concentration. So in this particular case, our finishing concentration is 0 and our starting concentration is 1 mole per liter. This is divided by 10 minutes, and in this particular case here for our water, we have finishing, which is 1 minus starting, which is 0, concentration divided by 10 minutes, and finally our oxygen, which is being formed, starts or finishes with 0.5 minus 0, which is the starting concentration, mole per liter, divided by 10 minutes. So that is about it for this particular case in here in terms of the rate of the overall reaction, which is, first of all, solving for this, we have 1/10. The other side here is 1/10, and this side here is actually 1/10 as well. But now, why is this actually 1/10? The reason why this is 1/10 is because since we had half here, so in this particular formula we have 1/2, which now becomes a 2 over there. So 2 times 0.5 is actually 1 in this particular case. So we have our rate of each of these particular reactants to the product to be that of 1/10, and in here we want to include our units. Our unit in here is mole over liter multiplied by mole multiplied by time, which is in minutes. So since this is actually happening, what we recognize is that mole cancels mole out, and what we get is 1 over liter minutes. So that is our unit for this particular rate in here. And take note that the reason for using this particular ln in this particular formula instead of log is because this log introduces an extra factor of 2.3, which is multiplied by that particular RT, which is the gas constant right here. Therefore decreases the activation energy, which is what we have right here, and as a result, little changes in the activation energy will result in greater exchange or change in the K value, which is what we have right there, which is the rate constant by close to 1 order of magnitude. 1 order of magnitude is usually 10 times. That is what it means for 1 order of magnitude in there. So that's about it for this particular video. Please hit the comment down below. Let me hear your thoughts. Think about this, explain it to your friends, and also believe in yourself right there.